Ladies and gentlemen, our final speaker in this session is Professor Toby Mottram. Toby is the Douglas Bomford Trust Professor of Mechanisation Management at the Royal Agricultural University at Cirencester. He just received a fellowship from BBSRC and the Royal Society of Edinburgh, which I understand is being taken at Cirencester. He's also founder and chief engineer of eCow, and it's on that topic that he's going to address us this afternoon, and it's to do with real-time rumen sensing. Toby, the floor is yours to talk about eCow real-time ruminant monitoring. Thank you.
Thanks. Well, I'm told that my microphone will switch on automatically from the back, so good example of wireless telemetry in action, and I can hear it is actually working. So, yeah, I am Toby Mottram, Douglas Bomford Trust Chair in Farm Mechanisation at the Royal, and I've been in that post since 2012. Since about 1995, when we commercialised and sold our robot milking technology to De Laval, I've been working on monitoring cows' health. If you take the human out of the milking system, you have to have some technology to monitor, because most of what a human does in a milking parlour, and I milked cows for 8 years, so I know this intuitively, most of what you do in a milking parlour is actually looking at things and monitoring cow health. But this talk is about the rumen bolus. This is something I developed over a number of years, and I founded eCow in 2007. The focus of this talk in this institution is about the engineering, because the question I was asked by the sponsors was to say, how do you get to where you are now? What were the challenges we overcame? What was the technology? I'm not going to put it all on slides, because some of it I don't particularly want to be broadcast to the planet, because we do have commercial competitors. So the main thing has been making this technology work. Now, the problem that we've been addressing is, how do we monitor the pH of the rumen? We've known for years that the pH is critical. This has been done with a technology called fistulation, where basically the surgeon cuts a hole in the side of a cow, and you can stick your hand in, you can put sensors in, and there are hundreds of those cows in the UK and tens of thousands probably around the world. But personally, it's something I think we should be able to stop doing very soon. If you like, our mission is to make invasive surgical procedures history by using wireless technology. So I'll show you next something that you won't see often in an engineering institution, which is a section through a dairy cow. It's all right, it's not, we didn't cut a cow in half for this, it's just a drawing. In commercial cows, the veterinary surgeons use a thing called ruminocentesis, which is basically, they get a big needle and they just stab the cow somewhere in here, and then they pull some rumen liquor out of the cow, and then they get their dodgy little sensor and put it on there and say, oh, pH is really low. Now, there's about 6 things wrong with that, and I won't go into the detail, and I hope there's not too many vets going to take offence, because they know themselves that this is not a good technique. But with that technique, we are told 30% of the cows, dairy cows in the United Kingdom, have subclinical rumen acidosis, SARA. Now, that's fine. It actually gives us a platform as to why we developed this technology. But I don't know where they take their samples from. Could be way down here in the reticulum. Could be up here where there's a lot of gas and methane and CO2, and you've got probably 0.2 pH lower than you would have in the middle point, or down here in the reticulum where we're actually slightly higher. And this, of course, is a constantly churning mass. The rumen's like a great peristaltic sort of machine that's churning away. So where are they taking it from? I don't know. But I know that if we make a specific gravity device, and there's a European standard for this because we did RFID by bolus, if it's specific gravity 2, it'll be in the reticulum. The Latin name tells you it retains things. Now, I first invented the pH bolus when I was back at Silso, 2003. We were asked by a biotech company to do the work, but the first versions weren't very good. They didn't last very long. And there's a simple reason for that. I'm going to get this piece of visual aid up here. Now, every pH sensor that's ever been used in a laboratory or in a process factory, it goes vertically downwards, okay? It's obvious. It's got a tip on the end. You stick it in the liquor. And that's just, that you just assume that's right. But hold on a minute. We've just built a bolus. It's going up and down and round about. Where do we, what direction is that sensor pointing? And what I suddenly realised was, if that sensor goes upside down, the air inside works its way out through the Teflon junction, the rumen liquor works its way in, sensor's dead in a few days. So that was a sort of a light bulb moment. And the other light bulb moment came when I was buying Christmas presents or something, and I saw a resin moulded paperweight with bits of electronics in, because we'd been having a lot of trouble with seals. You know, you make a tube of plastic, you put some electronics in, and then the rumen liquor works its way in, and your sensors die very quickly. So it was actually suddenly realising we could make this by moulding it, because your sensor has to be wet. So the bolus here, which I'm going to let you read those bits, because I'm going to start doing a little bit of drawing and doing a bit of engineering discussion. You've got the... Basically, a pH bulb is a measurement electrode with a piece of wire coming out of it. And then somewhere up here, you've got a reference electrode, which is silver chloride. And you have to have an electrical pathway to that sensor. Now, to the reference electrode, because you're comparing, if you like, that's 0, and that's whatever you're measuring, caused by the hydronium ions down here. So if you want to measure that circuit, you've got to have a liquid pathway. So we protect these with various Teflon frits. But over time, rumen liquor will work its way up through that. And that's been one of our major challenges. Of course, inverting it makes it a lot worse. So the first thing I did was actually to put a heavy weight around the end so that it always points downwards. We've got a patent on that. It's great. It's very difficult to get around that. You put your sensor in the bottom of a weight like a baby's bottle, and down it goes. Now, the next slide is showing you how our data flows. We love the smartphone. I heard the guy from class talking about tablets. Yeah, you don't have to build all that electronics that we used to have to do to put button boxes into the field. So basically, you go and stand next to your cow with a smartphone and a little dongle that we attach to it. Your data comes back into our server. Of course, the bolus can only hold a certain amount of data, so we actually concatenate it on the server. We can filter any issues that have come. We can spot when things are going wrong. And then you can get it from our server for aggregation, comparison, analysis. And these guys here, the vets and the nutritionists, they do the data interpretation. We don't tell people whether their cows are sick or not. We just let the vets and nutritionists. That is our route to the farmer. And they have been our great advocates. But it also brings you up against the most difficult challenge in agri-tech, and I'm glad that Willie's here, going to be able to talk us a little bit more about this. Metadata. We all talk about data, the Internet of Things. Oh, great, we're going to have all this data, but you've got to know what else is going on. Who's feeding the cows, when, what are they feeding them? So we've now got thousands of these daily pH profiles, but we haven't got that many bits of metadata. Now, here's a slide you won't see too often. We're going to tell you how boluses fail. This is nearly 7 months of data, starting in July. These daily profiles, will come back to those. If there's no data, if no one's gone to the cow, then you're going to get a gap in your data. There's a couple here where we didn't bother going to visit, or it's too long. We actually warrant the first 60 days. So this bit out here is all bonus as far as our customers are concerned. It keeps on working, but then slowly over time, something happens round about here. And this is what we call reference junction drift. And you can see that this slowly gets narrower and narrower and ends up round about 7. And that's exactly what we now know as reference junction drift. Because pH, if you go on a scale out to 7, 4 is where we usually do calibrations. This is millivolts. So when you get to 0, all instrumentation will be reading 7. So what's happened in this situation here is that this has now become contaminated and is going up and down at the same rate as this here. So effectively, there's a 0 millivolt potential. So that's how bolus sensors die. I'm probably spending a little bit too long on that, but I like that stuff. Right.
You've got a couple of minutes.
A couple of minutes, right. That's a cow with SARA, classic. Cows tend to sleep at night, pH rises, they eat in the morning, pH drops. This was a 12,000 litre herd, very, very successful herd, but they felt something was wrong. Put a bolus in, wow, we're going below 5.8 in the reticulum, that's bad. 2 weeks later, yeah, take a bit of high energy stuff out of the ration, milk yield doesn't suffer, the cows start eating more at night, they're actually doing a little bit more nibbling here, and you can see the range comes down and everybody's happy. The farmer takes about £6,000 out of his costs per month for the sake of a few cheap boluses, and yeah, we're happy. Right, veterinarians have been told for about 20 years that high-yielding cows are inherently likely to have SARA. But I think that's become dogma rather than data. So here we go. 7,000 litre cows. This is 2,000 data days. So in other words, with 96 data points a day, that's nearly 20,000 data points against the vet surveys with 200. So 7,000, 12,000. Now, if you think that's correlated, I don't know what to do. But you get a little bit more variation. There is a little bit of trend of percentage of time below 5.8. But actually, if you take one of those herds out, you'll get an R squared even lower than 0.46. So basically what this data says is that it's a farm-to-farm variation. There's nothing inherently likely to be wrong with high-yielding cows. So it's all about management, which is all about data. So just to finish up with, that's what we find, actually, if you overlay multiple days, the red line is the mean of all the data days. Cows want regularity. This is like a cloud. That poor cow doesn't know when she's going to be fed, what she's going to be fed. The nutrition was all perfectly well set up, but actually it's the farm management that counts. Different farm, much better results. You can almost lay those on top. Those cows are getting fed same stuff every day, same time. That's a bimodal, by the way. That's where they're feeding in the milking parlour. Right, Dick, how am I doing? Right, nearly there. Right. Okay, so we've spent about £500,000 over 7 years. First grant we ever had was from Smart Scotland. TSB and Innovate UK have been tremendous allies. I've put my life savings into this, which is the match funding, which has allowed us to generate this. We've got 7 employees doing high-tech manufacturing. We ship worldwide. In fact, 80% of the sales go overseas. Interestingly, we've never had an order from a UK institution. That says something. We're selling it to Vienna, Paris, Berlin. Why not the RVC? Why not Bristol? That's a question for those guys. I've got great hopes for the new experimental facilities we're going to get from the agri-epicentre. And in my next invention is going to be infertility monitoring, which comes from the Royal Society of Edinburgh. So that's my new fellowship, which I started last week. Thank you very much.